You're familiar with vectors and how to find the magnitude and direction angle of a vector. Just like with scalar quantities, a variety of mathematical operations can be performed with and upon vectors. Vector addition is one of these operations. Let's take a look at how this works as we continue to answer the question, how are vectors added and subtracted? We can relate vector addition to scalar multiplication. If we take a second vector with the same direction and magnitude as u, we can add them to get u plus u, or 2u. This applies to other scalars as well. So in other words, repeated addition is the same as scalar multiplication. Let's take a look at vectors u and v in the plane. We can rearrange these vectors by moving the tail, initial point, of one of the vectors to the head, terminal point, of the other in order to add them. Let's move the tail of v to the head of u. We can now draw the resultant vector by going from the tail of vector u to the head of vector v. A quick side note on notation, we will use the bold font notation throughout this lesson, but you might also see vectors written with an arrow over the name. This notation will be helpful if you are writing out vectors on paper. Let's now take a look at vectors u and v in the coordinate plane. We can rearrange these vectors by moving the tail of one vector to the head of the other in order to add them. Let's move the tail of v to the head of u. We can now draw the resultant vector by going from the tail of vector u to the head of vector v. We originally moved the tail of v to the head of u, but vector addition is commutative, so we can also move the tail of u to the head of v. As you can see, this produces the same resultant vector. We can also add the vectors algebraically in component form. Given u is equal to ab and v is equal to cd, we know that u plus v is equal to a plus c and b plus d. Let's take a look at the same vectors from before. U is equal to 4, 4, and v is equal to negative 5, 2. U plus v is equal to 4, 4 plus negative 5, 2. So u plus v has a horizontal component of 4 minus 5 and a vertical component of 4 plus 2, resulting in u plus v being the component vector negative 1, 6. You can see visually that the magnitude or length of individual vectors being added will not equal the magnitude of their sum. The only time they are the same is if the two vectors are in the same direction. Another way to do vector addition geometrically is by the parallelogram method. When we draw a parallelogram, we can see that the parallelogram outlines both possibilities of the head-to-tail method. The resultant vector is drawn from the origin. Vectors can be written and described in various ways. You have already been working with vectors and rectangular coordinates in component form. with A being the horizontal component and B being the vertical component. We will also be working with vectors in polar form. With polar coordinates, the radius from the origin, denoted as r, is the magnitude or length of the vector, and the angle theta is the direction of the vector. Polar coordinates of a vector in component form are written in horizontal components as r cosine theta and the vertical component as r sine theta. Since we can relate vector operation to triangles, we can use the law of cosines and the law of sines to help us operate on vectors. We can use the law of cosines to find a resultant vector magnitude or length, and we can use the law of sines to find the direction angle of a resultant vector. Given vectors u and v, we can use the law of cosines to find the magnitude of the resultant vector. First, we want to find the angle between the vector's initial points. We do this by subtracting the direction angles of the vectors. So the angle between their initial points is 45 degrees. We can use the properties of a parallelogram to determine the actual angle between the vectors, theta. The resultant vector, w, is the diagonal of the parallelogram, so we know that theta is 180 minus 45, or 135 degrees. Now that we know the angle between the vectors, we can use the law of cosines to find the magnitude of vector w. We can substitute in the values we know, simplify what we get, 64 plus 36 minus 96 times negative the square root of 2 over 2. And when we continue to simplify, we see that the magnitude of w is approximately 13 units. The direction angle for the resultant vector, w, is 30 plus alpha. To find alpha, we'll use the law of sines. Cross-multiplying, we get 13 times sine alpha is equal to 6 sine 135 degrees. Then, solving for sine alpha, we get 6 divided by 13 times sine 135 degrees, which we know is the square root of 2 divided by 2. We'll use the calculator to find the approximate value. The inverse sine of that value is approximately 19 degrees. This makes the direction angle for vector w 30 plus 19, which is 49 degrees. Alternatively, you could have converted from polar form to rectangular form to add the components. The x component of the vector is r cosine theta, and the y component is r sine theta. We can substitute in the values we know. The component form of w has an x component of 8.482 and a y component of 9.796. When we convert back to polar form, we see that the magnitude of w is approximately 13 units and the direction angle is 49 degrees, which is what we expected. We're answering the lesson question, how are vectors added and subtracted? You've learned the methods to add vectors algebraically and geometrically. You have also found that multiplying a vector by a negative value reverses its direction. Now we will connect these concepts and look at vector subtraction and other additional vector operations. Let's take a moment to talk about a special type of vector. A vector with a magnitude of 1 is known as a unit vector. A vector can always be multiplied by some scalar, resulting in a unit vector that has the same direction as the original vector. Multiplying a vector by the reciprocal of its magnitude, which is a positive scalar, will produce a vector in the same direction. In component form, vector v is 3, 4. So its magnitude is 5. And the reciprocal of its magnitude is 1/5. We can use the distributive property of scalar multiplication to produce a unit vector of 3/5, 4/5 that is in the same direction as v. Vectors I and j are special unit vectors. Vector I is the length of 1 on the x-axis, and vector j is the length of 1 on the y-axis. These vectors are useful, as they help us write vectors in another notation. V is a vector with an x component of length a and a y component of length b. Factoring those components out leaves us with the scalar values times the special unit vectors. We can then replace their component form with I and j. The vector v is now written as a linear combination of the unit vectors I and j. Let's now take a look once again at vectors u and v in the coordinate plane. What is u minus v? Well, let's take a look at it in terms we know. Just like with scalar arithmetic, we can rewrite u minus v as u plus negative v. We know that negative v has the same magnitude as v, but its direction is opposite. Now, we can use one of the addition methods to draw the resultant vector. We can also subtract vectors algebraically in component form. Given u is equal to ab and v is equal to cd, we know that u minus v is equal to a minus c and b minus d. Let's look at vectors on this plane. U is equal to -6, 2, and v is equal to 1, -5. U minus v is equal to -6, 2, minus 1, and -5. So u minus v has a horizontal component of -6 minus 1 and a vertical component of 2 minus -5, resulting in u minus v being the component vector -7, 7, which we can also see on the coordinate plane. Also note that vector subtraction is not commutative. U minus v does not equal v minus u. We just saw that u minus v is equal to -7, 7. But v minus u has a horizontal component of 1 minus -6 and a vertical component of -5 minus 2. Therefore, v minus u would equal 7, -7. We can also subtract vectors in polar form. Let's first convert from polar form to rectangular form. The x component of a vector is r cosine theta, and the y component is r sine theta. We can substitute in the values we know. The component form of u minus v has an x component of 1.536 and a y component of 10.66. When we convert back to polar form, we see that the magnitude of u minus v is approximately 10.77 units, and the directional angle is 81.8 degrees. Multiple operations can be performed on vectors including addition, subtraction, and scalar multiplication. The sum of two vectors is a vector, and the product of a scalar and a vector is also a vector. Let's try it out. In this situation, we are presented with three vectors, u, v, and w. We're asked to simplify the expression u minus 2v plus 5w. Let's first begin by finding 2v and 5w. 2v is equal to 2 times negative 8, comma 2, which equals negative 16, 4. 5w is equal to 5 times 1 and 1, which equals 5, 5. Now we can substitute these values into our expression. We get 0, 7 plus 16 and negative 4 plus 5, 5. Adding the horizontal components gives us 0 plus 16 plus 5, and adding the vertical components gives us 7 minus 4 plus 5. Simplifying, we get 21, 8.